Welcome.
My name is Mohammed Karol Ridwan bin Khairul Anur. My matrix number is 251,091,622. I want to present for ENJ120 to my presentation is about perovskite materials for photovoltaic solar cells. As the global demand for clean energy grows, photovoltaic technology, which converts sunlight directly into electricity, has become critically important. For decades, silicon-based solar cells have dominated the market. However, their high manufacturing costs, rigidity, and efficiency limitations have driven the search for alternatives. This is where perovskite solar cells emerge as a groundbreaking solution. Since their introduction, perovskites have seen a phenomenal rise in efficiency, soaring from just a few percent to over 22% in certified lab tests, rivaling and sometimes surpassing traditional silicon cells. This rapid progress positions them as a key player in the future of solar energy. So, what exactly are perovskites? Their unique properties stem from their crystal structure, which has a general chemical formula of ABX3. In this structure, A and B are cations of different sizes, and X is an anion that bonds them together. This versatile structure gives perovskites remarkable physical properties. One of the most significant is a tunable band gap, which allows scientists to adjust the material to absorb different parts of the solar spectrum, maximizing energy capture. They also possess a very high absorption coefficient, meaning a very thin layer of perovskite material can absorb as much sunlight as a much thicker layer of silicon. From a mechanical standpoint, perovskites offer incredible flexibility. Unlike rigid silicon wafers, perovskite thin films can be deposited on flexible substrates like plastics or even textiles. This opens up possibilities for bendable solar panels and integration into wearable technology. Electrically, perovskites are just as impressive. They exhibit the long charge carrier diffusion length, which means that electrons and holes generated by sunlight can travel far within the material before recombining. This increases the chances they will be collected as electrical current. Furthermore, their ambipolar transport properties allow both positive and negative charges to move efficiently, contributing to the overall high performance of the solar cell. Despite their impressive electrical and optical properties, perovskites face a significant hurdle: stability. They are notoriously sensitive to environmental factors, particularly heat and humidity. For instance, the commonly used perovskite compound, methylammonium lead iodide, or MAPB, tends to decompose when exposed to moisture and elevated temperatures, leading to a rapid decline in performance. Researchers are actively working to overcome this. One promising approach is replacing the volatile methylammonium cation with more stable formamidinium, or Fa+ cations. This substitution has been shown to improve materials' thermal stability. Another challenge lies in manufacturing. The high temperatures required to process certain electron transport layers can damage the sensitive perovskite layer underneath, complicating large-scale production. The unique properties of perovskites unlock a wide range of exciting applications beyond traditional solar farms. Their flexibility makes them ideal for manufacturing lightweight, bendable solar panels that can be rolled up and easily transported or integrated into curved surfaces on buildings and vehicles. This also extends to wearable electronics and smart textiles, where perovskite solar cells could be woven into fabric to power personal devices on the go. One of the most promising applications is in tandem solar cells. By layering a perovskite cell on top of a traditional silicon cell, we can create a device that captures a broader range of the solar spectrum. The perovskite layer absorbs high-energy blue light, while the silicon layer absorbs low-energy red light, boosting the overall efficiency beyond what either material could achieve alone. Beyond solar cells, perovskites are also being explored for use in LEDs, photodetectors, and other portable electronics, all benefiting from their low-cost, solution-based fabrication methods that pave the way for large-scale commercialization. To address environmental concerns, particularly the toxicity of lead, significant research is focused on developing lead-free perovskites. Materials like barium tin sulfide are being investigated as safer, more sustainable alternatives. Simultaneously, advancements in manufacturing techniques such as vapor phase deposition are helping to create more stable and uniform perovskite films, reducing waste and improving the longevity. These efforts aim to combine high efficiency with improved sustainability, ensuring that next-generation solar technology is not only powerful but also environmentally responsible. The goal is to create a solar technology that is highly efficient and has a minimal environmental footprint throughout its life cycle. However, several challenges still need to be addressed before widespread commercialization. Long-term stability remains the primary concern, as devices must withstand decades of outdoor exposure. Another issue is JV hysteresis, where the measured efficiency of the cell depends on the direction of the voltage scan, complicating performance evaluation. The toxicity of lead in the most efficient perovskites necessitates robust encapsulation strategies to prevent leakage and the development of effective end-of-life recycling processes to manage waste responsibly. Overcoming these hurdles is the final frontier for perovskite researchers. In conclusion, this exploration of perovskite materials has highlighted the critical relationship between a material's structure, its properties, and its performance in a real-world application. Studying this topic has reinforced the importance of independent learning and critical thinking in solving complex engineering problems. Perovskite solar cells represent a frontier of materials science with immense potential. While challenges remain, continued innovation in materials design and device engineering promises to unlock a future where clean, affordable, and versatile solar energy is accessible to all. Thank you.